We spent the first part of this chapter talking through the Diels-Alder reaction, but there are many reactions that occur through concerted mechanisms with cyclic intermediates. Take, for example, this reaction between an alkene and osmium tetroxide that makes cis-diols. The osmium tetroxide is able to provide two sets of pi electrons, one from each double bond to oxygen. The alkene provides two of its own pi electrons to perform a 4+2 cycloaddition. Notice that in this case, the diene isn't a diene at all. It's two carbonyls on an osmium which get reduced. But because this reaction occurs through a concerted cycloaddition, the alcohols that are formed will always be cis. A use note for this particular reaction, osmium tetroxide is super toxic, so it's always used catalytically, and the hydrogen peroxide that are used is to regenerate the osmium tetroxide in solution. We can do a similar but less toxic reaction with potassium permanganate. The permanganate will also proceed through a 4+2 cycloaddition, leaving a cis-diol. However, the permanganate remains strongly oxidizing and the alcohols remain oxidizable, so yields tend to be low with this reaction, even at really low temperatures. Yields are slightly higher for the alkyne, where the permanganate can give two separate cycloadditions for a total of 4 alcohols. The geminal diols, in case you don't remember, that's what we call two alcohols on the same carbon, can each eliminate a water through the chapter 17 and 18 mechanisms we talked about to yield a diketone, this time in really excellent yields. With a little more energy, permanganate can go through a slightly different reaction after the initial cycloaddition, a cycloelimination. Despite the sound of that, these are not the reverse of each other, and the resulting product is oxidative cleavage. We break both sides of the alkene or the alkyne apart into two carbonyls. You can kind of think of this as the opposite of a Wittig reaction. Here's an example. When permanganate is reacted with an alkene, noting now the higher temperature, the alkene is split and both sides are oxidized to their highest oxidation state. The carbon that begins tertiary loses the bonds to the other alkene carbon and becomes a secondary ketone, while the carbon that was initially secondary loses both bonds to the other alkene carbon and gets oxidized all the way to a carboxylic acid. All of this happens in the initial basic conditions, with acidic workup serving really just to quench the reaction and convert the carboxylate that's formed in base back to a carboxylic acid. The initial mechanism is exactly what we saw for osmium tetroxide, again a 4+2 cycloaddition. However, the permanganate can also be removed by cycloelimination. This step doesn't change the manganese formal charge, but is a reduction in oxidation state. Although the aldehyde is initially formed, the aldehyde is easily oxidized with any excess permanganate, and the carboxylic acid is ultimately the product that forms. Permanganate isn't the only reactant that can perform oxidative cleavage through a cycloelimination. The same thing can be accomplished in any 1,2-diol using periodate, or IO4-. These reactions are distinct because they will not oxidize aldehydes that are formed in the reaction, so we end up with an aldehyde product instead of the carboxylic acid product. The reaction as written oxidizes an alkene to a diol with osmium tetroxide, but if the diol is available in any other way, we can start directly from the diol too. The diol is able to form a diester with periodate through several steps, and the periodate is reductively eliminated as iodic acid by the same mechanism as the permanganate elimination, leaving the oxidatively cleaved product. Periodate doesn't readily oxidize aldehydes, so the aldehyde is maintained in the product. The oxidative cleavage with periodate is fine for an existing 1,2-diol, or even for an alkene if you hate our world, but generally it's much better to use more benign reactants where possible. We can actually use ozone, O3, to oxidatively cleave alkenes as well, through a set of similar but much greener reactions. The initial cycloaddition is a 4+2 cycloaddition again, with the molozanide product initially formed, quickly cycloeliminating to form a ketone and a reactive ketoperoxide derivative. This can proceed through another cycloaddition. Note that the carbonyl electrons on the left are really only able to donate because the O- is adding electrons at the same time to form the much more stable ozonide. Several reductants can be used to break down the ozonide. Dimethyl sulfide, DMS, as shown, or metallic zinc and acetic acid are both fairly common. In synthesis, Diels-Alder reactions are really effective at forming rings, so the ring itself can be an important indicator of a possible Diels-Alder product. More importantly, the Diels-Alder reactions will always leave at least one alkene, which can further react to form all sorts of other products. When you see a ring in a functional group, especially an alkene, but really any functional group, that functional group may have originated with an alkene from a Diels-Alder. Diels-Alders are not the only way that we can form rings, but they do have some of the mildest conditions. Here's an example of a Diels-Alder reaction that uses a resulting alkene to cleave and form aldehydes that can then go through an aldol condensation to form an entirely new ring. Diels-Alder reactions are incredibly versatile in synthesis because of the amount of stereochemical and regiocontrol that is possible. For example, the Diels-Alder shown in this cholesterol synthesis is able to generate the proper stereochemistry while also forming the ring at the same time. It is easy to think about the pericyclic reactions as an artifact that are unique to laboratory synthesis. The cocoic acids, which are from the coca plant but unrelated to cocaine, form naturally by 2+2 photoadditions of cinnamic acid. Our greenhouse chemistry lab is actually the forming of one of these products. But alas, COVID-19 strikes again. Another great example is the shikimate pathway, which is responsible for forming certain aromatic amino acids. It is not used in humans where these amino acids are essential and need to be supplied through our diets. The pathway is, however, used in many plants and bacteria and is the target of glyphosate, the active ingredient in the weed killer Roundup, which kills off many plants and also certain bacteria. But I digress. This enzyme is not the target of glyphosate, but it does catalyze the pericyclic rearrangement of charismate later in the pathway. Pause and see if you can generate the appropriate arrows for the reaction before I make them magically appear. Like magic, but infinitely easier to do on the board. We can use a lot of the same logic that we talked about with Diels-Alder reactions to explain this reaction, like why the enyl pyruvate group on top is arranged the way it is. The carboxylate wants to align with the conjugated system, and the enyl has more negative charge at the position with the arrow where the arrow is drawn out. The location to which the arrow is drawn is more positive because of the neighboring carboxylate, our fairy tale ending for our pericyclic reactions. As usual, we'll end with a text summary of the chapter that complements the reaction tables that are at the end of the chapter. Make sure you understand both the reaction tables and the context for those reactions as we discussed in this lecture.